Okay, in the past couple videos, we looked at the wave functions, the mathematical description for these wave functions, and their behavior for a one-dimensional particle in the box. However, as we start to think about electrons, electron distribution, and electron configuration within an atom, we want to think about this in 3 dimensions. Okay, so instead of solving for a one-dimensional particle in the box, we can instead solve for a 3-dimensional particle in the box. We're not going to go through the math from that, but much in the same way as the one-dimensional particle in the box results in a quantum number n, which we can then use, that helps to describe both the energies and the wave functions. The 3-dimensional particle in the box will also result in quantum numbers. Okay? In this case, it's going to result in 4 quantum numbers, and we're going to show what these, we're going to introduce these here. Okay? So first, we'll have the symbol, and so much like for the one-dimensional particle in the box, which had a principal quantum number, which we termed n, we still have that quantum number for the 3-dimensional particle in the box. And so this is, oops, the principal. And then I'm going to shorthand this as Qn. Okay? And so values, allowed values for the principal quantum number are any positive integer. Okay? So for instance, 1, 2, 3, all the way up to any number n. Okay? And so this term has the largest effect on energy of the electron. Okay? So higher values of n mean higher energy. Okay? The next one is lowercase l. This is the angular momentum quantum number. Ooh. Switch this up. Okay. And so these values will range, again, these will be anywhere from 0 to n minus 1. Okay. So that means if an electron has a principal quantum number of 2, right, then the highest value of L it can have is 1. Okay, but it could be either 1 or it can be 0. The L quantum number for that particular electron in an, with an n equals 2 principal quantum number could be 0 or 1. Okay, and so this actually relates to the atomic orbitals, which we'll talk about, which we'll review again very soon, where L, right, for an s orbital, L is equal to 0. For a p orbital, L is equal to 1. For a d orbital, L is equal to 2. An f orbital, L is equal to 3, and this continues on and on. Okay? And so what this tells you is the angular dependence. Or more simply put, the shape, okay, of the orbital that the electron resides in. All right? Then we have m sub L. This is the magnetic quantum number. All right? And this ranges from, depending on what the L value is for this electron. Okay, so you see there's kind of a hierarchy that's being established here where n dictates the value of L dictates the value of m sub L. Okay, and so m sub L can range from anywhere from negative L to positive L. All right. And this tells about the electron orientation in space. Okay. Oops. All Right, the final quantum number is m sub s. This is the spin quantum number. All right, and these can only have values of +1/2 or -1/2. Okay? And this tells you about the internal spin of the electron. Okay? And so by using these 4 quantum numbers, we can describe any electron in an atom. So another way to say that is each electron within an atom has a set of these 4 quantum numbers, and they are unique for each electron within an atom. And so we can accurately describe each electron within an atom or later on within a molecule using this information.